Okay, we're back. We're going to start taking a look at how we come up with the location of the ellipse. I mean the focus of the ellipse uh, with the major and minor axes values given. Okay, so we're going to look here. We're going to go back to our definition, which of course stated that any point is the sum of that point to one focus plus that point to the other focus was always equal to 2a, or the length of the major axes, okay? So therefore, we agree that regardless of where we swing this point around, this point G, wherever we swing that, okay, uh, when we add the distance from that point to one focus and that point to the other focus, it will always be a constant value, and in fact will always be 2a. So I'm going to go here to I'm going to go back to our my geometry sketch pad to illustrate that. Okay, again, point B, a point on the ellipse, is always 2a distance away. Okay, here my 2a is 10. The sum of that distance is always 10. Whether it's here, here, or in fact, right up here at point D, which is at the point 40. So the reason why I swing it around here is because now I can look at the right triangle. I can look at the right triangle, which is made with the segment, okay, GF, okay, F and F1 or F and F2, and the hypotenuse, okay? So what's the hypotenuse length? Well, the hypotenuse length in this position, as you can see, okay, is, all right, is exactly equal to the A value, okay? My exact equal to the A. Remember, the sum of these two lengths, BF1 and BF2, will always be 10. Will always be equal to 2a, generally speaking. Here it's equal to 10, so generally speaking, it's always going to equal 2a. So if I swing it up to this position, BF1 plus BF2 will still equal 2a, but since I have congruent triangles here, I'm going to conclude that my length, BF1 or BF2, is in fact A. Okay? Now, if that's A, then you should agree that the distance GF is the length of half of the minor axis, which is going to be B, okay? So, and you can see that that is 3. So then you can see if we call the hypotenuse A, because it is half the major axis, the length GFB, okay, then the distance to my foci is going to be C, and by Pythagoras, I'm going to have, okay, A squared, which is this, in this case, the hypotenuse, is going to equal B squared plus C squared. So don't get that mixed up with the A squared plus B squared equals C squared. It's a little bit different. It's C squared plus A plus B squared equals A squared. So let me go back and show you that here, okay? We're going to go back on my PowerPoint to illustrate that again here. So here's my right triangle, as you can see here, okay? Let me just pull that up. Here's my right triangle, and this is what we're meaning to show, okay? So we obviously have a right triangle here. BC, as we agreed, okay, from the previous geometry sketchpad model, was going to be equal to A, okay? So BC and B, since they're congruent, BC and BC prime are both equal, in this case, both equal to A, okay? PB is the minor axes, half the minor axes, okay? And by right triangulation, by Pythagoras, we agree that BC squared is equal to PC squared plus PB squared, as you can see right here, okay? But recalling, BC is half the major axes. That's what I'm going to call my A, since My A values always help me to define where my major axes were in my ellipse, okay? PB is going to be half my minor axes, calling that B, and C is going to be the focal distance, that is the distance from the center of the ellipse to the focus on either side, okay? And so therefore, I'm going to get, okay, for the value of my ellipse, for any of my ellipses, the center, or I'm sorry, the focus is at a coordinate given by the square root of a squared minus b squared. So that is how we come up with the focus or focal length for the ellipse. We went through all that, okay? Now we're going to talk about the eccentricity, okay? So the eccentricity is going to be regardless of the orientation. The eccentricity, as I said in an earlier video, was how the ellipse varied from that of a circle. So it's going to be a ratio. The ratio of for the eccentricity is simply the focal length over the major axes. The focal length, okay, from the center out to the vertex divided by the focal length from the center out to the focus divided by the semi-major axes divided by A. C over A is the eccentricity. C over A is the eccentricity, okay? So the further C drifts out, as we saw in the Desmos, the flatter this gets, the more elliptical that gets, and therefore the closer that is going to get to 1. So eccentricities for very flat ellipses are going to approach 1. Eccentricities for more circular ellipses are going to approach 0. So the circle is an ellipse of eccentricity 0. So like I say, if A is equal to B, then the ellipse is a circle and the eccentricity is 0. Okay? So we'll go and look at some examples in yet another video. Okay? That'll do.